Suppose it's an assignment where you had to curve fit a bunch of points. Unfortunately, you seem to have forgotten how to do a linear regression in Excel. Luckily for you, you happen to know how to make a genetic algorithm. But what exactly is a genetic algorithm? Well, this is basically a system of random guessing inspired by natural selection. A set of solutions are made to compete over several generations, and hopefully, at the end of all the bloodshed, we hope that there rises the most optimized solution. So here is the code for the program. Most of the code was written by me with the help of the MATLAB documentation, but I did use one thread to assist me in trying to figure out the sort function. So, the program consists of 4 functions, a main script, and 2 classes. The specimen class contains the DNA and functions to construct it, create the DNA, evaluate the DNA, and rank the DNA. The other class is a mutator class. This contains all 3 algorithms needed to manipulate the DNA in the specimen class. It should be noted that the other 4 functions mainly deal with the user interface and the configurations. So now let's roll the program out. If we just click run. So now we're greeted with a GUI. We can configure the program. We can use sample data, which is hard-coded values in the program, or alternatively, we can import from Excel. This screen currently shows the best specimen in the generation. If we let the program run, we can see that over 250 generations, the curve fit gets much better. 3 phases were planned before the creation of the program. The first phase was simply to create a program that will be able to graph a randomly generated version of DNA. The second phase had a goal to implement the genetic algorithms and have the DNA mutate over the generations. Finally, the last phase was simply to improve the user interface so that it would be accessible and easier to use. So here is an earlier version of the program, and it only has the specimen class. However, by running the program, we can see that I was able to successfully code the DNA system. Hi everyone, welcome to Lion Academy, and today we will be looking at the makings of a genetic algorithm, and more specifically, the evolutionary grapher. In order to make a genetic algorithm, one of the key components is the DNA. DNA holds the properties that a specimen will express, and in this program, the DNA is in the form of a matrix that looks like this. Now, you may be asking, how can this DNA matrix be expressed as a graph? Well, that's a very good question to ask, and the key concept is that the matrix holds the parameters to a polynomial that looks like this. Now, this notation might be a bit hard to understand, so let's give an example. Okay, so here we have an example matrix that could be inside a specimen. Using the above format, here, we can turn the matrix into an equation. Now, when it comes to graph this equation, what the program will do is actually add them all up. And so, this is the equation that the program will graph. One of the reasons that I stored the DNA in a matrix is because the vectorization will really help in mutating the DNA since it is much faster than using traditional loops, thus cutting down on the program's runtime. Now that we have a DNA, the next thing we need to be able to do is cause mutations to produce a better specimen. Mutations alter the DNA using specific algorithms to produce hopefully better results than the original. In this program, there are 3 mutation types used. The first is the random mutation. The random mutation will essentially take in a DNA matrix, add a random number to every single term except the first column, and then output a new matrix. So an example of that would be, if the random mutation function takes in the above matrix, we would get. As you can see, there is no specific pattern in the matrix. The next mutation type is the merge mutation. Merge mutation will basically take one row of a DNA matrix, add it to another row of a DNA matrix, and then take the average of both. It should be noted that the program will only add rows together if their degree, that is, the number in the first column, is the same for both rows. If these 2 matrices were used in merge mutation, the output would be. The third and final mutation type in the program is selection mutation. What selection mutation will do is that it will take in 2 DNA matrices. One of them will be dominant and the other will be non-dominant. During the mutation, the program will run a loop through every single row in the non-dominant DNA. 50% of those times, the program will replace one row of the non-dominant DNA with the corresponding row in the dominant DNA. As such, the resulting DNA output would be